Let's start off this new section in physics with a little history lesson. It turns out that in ancient Greece, a random experiment was found. They found that if you take two pieces of amber, amber is just a fancy term for dried tree sap. So if you take two pieces of amber and you rub them with a cloth, then these two pieces of amber will repel each other. Kind of an interesting experiment, which you can actually do today. If you have a piece of plastic, you can rub it with a cloth and then suspend it. Grab another piece of plastic, rub it with a cloth, and you should be able to get a similar effect. Now, here's the interesting thing about this old experiment. The Greek word for amber is actually electron. So when you talk about electrons, you're really talking about amber or dried tree sap. No, not really, but that's where the root of this word came from. It came from the effect that happens when you have two pieces of amber that start to repel each other. You can get a similar effect at home. Everyone's done at least something like this. They've taken a balloon and rubbed it through their hair, causes the hair to stand on edge. You take a comb, run it through your hair, and then you can either bring the comb close to a sink faucet, and it causes the stream of water to divert. It doesn't go straight down. It kind of curves and bends down. Or you can use the comb that you ran through your hair to pick up small pieces of paper off of the table. And everyone who has a little brother's done this one. You drag your sock-covered feet across a carpet. You walk up to your little brother and you zap them. Same principle that's happening with the amber. Well, we discovered quite a bit about it, and over the many centuries after the ancient Greeks, we started to see a little more of the importance of this amber effect. Well, there's an American physicist by the name of Benjamin Franklin. Yes, the Benjamin Franklin. Everyone knows him. He's famous for the famous kite experiment, where he flew a kite in the middle of a thunderstorm. We have no idea if that was a real experiment or not. We just don't. But he did do a lot of experimentation with electricity, or the electron effect. And he classified, they had decided that that the reason you have this amber effect, some things repels, other things attract, you're going to have different characteristics, and they call those characteristics charges. Benjamin Franklin is the one that denoted the positive characteristic, or positive charge, and the negative characteristic. So whenever we talk about plus or minus charges, it's Benjamin Franklin who came up with that. So there were two types of charges, positive and negative, and what we found was that if you have two like charges, such as two negatively charged or two positively charged, come close to each other, they will repel. That's what happened way back here with the amber effect. Since amber means electron, we can gather from that, and it is accurate, by rubbing the amber with a cloth, you charged the amber with negative charges. And so basically, this was your amber effect right here. This is what happened. But they also noticed that if you have two opposite characteristics, or opposite charges, that they started to attract. An important rule about charge is that electric charge is conserved, meaning the arithmetic sum of the total charge cannot change. So let's say that you have two boxes next to each other. They are neutrally charged. There is no charge at all. But then you do something, and we can explain in future videos how this is possible. But this one, let's say that you have a charge of positive 3. Then down here, the charge in the other box has to be minus 3. Why? Because your initial total charge was 0, And so your total charge afterwards has to be the same. It has to stay at 0. If I had said that this box had a charge of +2, then I would need my total charge in the end to be 2 as well. So this would be a charge of -1. And that would give us a total charge of 2. So where does this charge come from? In the days of Benjamin Franklin, we didn't know for sure. But in the early 1800s, scientists by the name of John Dalton came up with the atomic theory. And that atomic theory was developed and enhanced and not perfected, but it was made more accurate until we have this rough diagram of an atom where we say that there's a center to the atom made of protons and neutrons. Protons are what give the nucleus a positive charge, and you have electrons orbiting around the positively charged nucleus. If you go in and talk about quantum physics, you can get a more accurate representation of the model of an atom. But this suffices for our discussion on electricity. So normally, an atom is electrically neutral, meaning whatever charge you have in the center, you're going to have an equal amount of charge in your electron cloud, the number of electrons orbiting around the nucleus. So in this case, we have 3 positive charges in the nucleus. You have 3 electrons orbiting around it. That would give you an electrically neutral atom. But if you rub objects together, then that causes electrons to move from one object to another. So if we go back to the amber effect, you have this cloth that you're rubbing around a piece of amber. Well, what's happening is electrons are moving from the cloth into the amber, leaving the amber negatively charged and the cloth positively charged. Okay. And so by conservation of charge, the total amount of charge in both has to be equal. And when you take the positively charged cloth away, that means that your amber, or in this case your stick, remains negatively charged. Now, you can have an electrically neutral particle or molecule and yet still have an apparent charge. Here you have a molecule of water. Hydrogen has 1 proton, so let me draw in a positive charge, and hydrogen, which is a positive charge, and an oxygen molecule, which has 6 protons. So the whole molecule is going to have 6 plus 1 plus 1, or 8 electrons. Well, we're going to see those electrons. Here, let me draw negatives. And they look something like this, more or less. Well, what happened? Well, with the hydrogen molecules, all the electrons are on the side of the atom that's connected with the oxygen, which means this side remains has an apparent positive charge, because all the electrons are on the other side of the atom. Likewise, with the oxygen, there are more electrons over here on this side of the oxygen, and so you have an apparent negative charge on that side of the molecule. So water is something we call a polar molecule, which is neutral overall, but because the charge is not evenly distributed, you have one side that comes out positively charged, the other side becomes negatively charged. Now we measure charge in a unit that's called a coulomb. We're going to meet coulomb in the next few videos when we talk about electric forces. But this is the basic unit of charge. Now when you take the amber effect, where you have an amber rod or a comb running through the hair, Charges that are produced by rubbing are typically around a microcoulomb. That's 10 to the minus 6th microcoulombs. Often in our class, in our course this semester, we will be dealing with 30, 40, 50, 60 microcoulombs, something like that. So what causes charge? Well, we saw back here that charge came from a separation of electrons from their nuclei. And so as a result, we can say that all electric charge is quantized in units of electric charge. What that means is that any charge Q, which is the variable we're going to use for electric charge, any charge Q is going to be some whole number multiple of the charge of an electron. And the charge of an electron is found right here. It's about 1.602 times 10 to the minus 12 coulombs. Any electric charge we deal with this semester or in the real world anywhere has to be some whole number multiple of the charge of an electron.